my talk is I like to answer those three questions: why, how, and what. Okay, that's probably a bit too general. So to make it a bit more specific, so why do we actually model the ocean? Why is it really important to understand oceans on climate timescales? And what is so complicated about that? So the second part will be sort of try to answer the question, how do we model the ocean? And the last part, what do we achieve? So where we are at the moment and how does different projects already are aligned to Deep South initiatives. All right, that is my most famous, or no, my favorite figure. Probably a lot of people know the statement on the top, so improving climate predictions for New Zealand. So that is, I think, at least for me personally, the major goal of the Deep South National Science Challenge. So we try to improve our predictions, future prediction, climate predictions for New Zealand. And this figure now shows something, I would call it climate sensitivity. And there are different parts of the Earth system mapped underneath. And for me, climate is sort of from here to the next 100 years. That is what I understand is the climate time span. And now you see where certain components of the Earth system are influencing this system. So, and not really surprising, so ocean is one of those main drivers. Sea ice, biosphere. I don't know why the atmosphere is actually so short. I think that's slightly biased. So I got this figure from World Ocean Review. So maybe they pushed it a bit further. Anyway, oceans are important on those time scales. So ENSO, all decadal oscillations are happening, are really important, and oceans are important. So why is this the case? Simply because of oceans are a massive heat reservoir, and they have the ability to move this heat around. This figure shows now the Earth's heat balance. So we know the tropical regions, low latitudes have they gain heat, solar radiation, and there's a deficit in higher latitudes. And now those regions, tropical regions, don't heat up excessively. There must be something like a heat transport. And that is actually facilitated or accomplished by atmosphere and ocean. And to the large part, the atmosphere is contributing to that. I think in some regions, 2/3 to 1/3. But also the ocean can carry large amounts of heat around the globe. And especially, for example, or just to illustrate here, that is the large-scale overturning circulation from an Antarctic point of view. We, for example, know that approximately 90% of all global heat due to climate change end up in the ocean on long time scales. And that is simply because the ocean has the ability to store heat and carry it around and sort of also re-emerge it at later stages, for example. A good example is also that, for example, the first 2 meters of the ocean surface have the same thermal capacity like the entire atmosphere above. And we know there are not only 2 meters, there are a couple of kilometers usually in most cases. All right, so it's a heat sink, and it's also important for carbon uptake, especially the Southern Ocean. That is one of those hotspots where anthropogenic carbon can enter the ocean because deep water is formed. At the moment, numbers are around 2 petagram carbon per year. And that is also the reason why we focus so much on the Southern Ocean. The Southern Ocean is a connector, so it connects all different world oceans, and it acts a bit like, unfortunately, like a washing machine, which makes it complicated, but at the same time also exciting. All right, another interesting story which I briefly like to touch on. I attended recently a conference, GWEX conference, for people which are not familiar in this space. So that is one of those subgroups of World Climate Research Program. And this group, which is usually quite atmosphere focused, so they try to model or analyze energy budgets and global energy budgets and hydrological cycle over the past years, they recently had a bit of a review and thought, maybe we have to rethink our long-term strategies. And it was really surprising to see that what they came up with. And now, where does the heat go and where does the CO2 go? That is their long-term vision, what they tried to understand. And if you paid attention to my previous slide, you know what they have to consider as well. All right, so now I come shortly to the point, why is it so complicated to model the ocean? And I will try to start the animation. Shown is here sea surface speed in a global eddy-permitting configuration. Sea surface speed, so it shows ocean currents. You see a lot of variability in tropical regions and a lot of variability also in western boundary currents. For example, now in the Argo region at the bottom. And it turns out there are a lot of mesoscale activity everywhere, and especially in the Southern Ocean. So, and unfortunately, still a lot of models are not able to simulate eddies or those mesoscale eddies explicitly, or struggle, or they have parameterizations, but to be honest, they are not doing a really good job to simulate the effect of eddies. All right. So there are eddies, and my title of my talk was what is happening below the surface. Before I start the next animation, I like to describe it, because otherwise you're not probably hard to understand. So shown is sea surface or temperature at the various depths. So we move slowly down into a water column, and the simulation starts from January to December and then jumps back to January, and we go depths further down. So you see, for example, now the seasonal cycle, as it goes throughout the year, and now we slowly go down into the water column. So we are at the moment 417 meters, and there are still a lot of mesoscale activities. All these small wiggles around New Zealand, for example, in the tropical regions, in the Southern Ocean, they are still persistent, and now we slowly get into deeper ocean, or first 200 meters or so, and you see that the seasonal cycle becomes less pronounced, but there are still in a lot of locations a lot of mesoscale activities, small eddies, and they are important to carry heat, nutrients, all kinds of stuff around, and really important for modeling the ocean realistic. All right, so which brings us now to the Earth system model. You probably are familiar with that. So the New Zealand Earth system model tries to model the entire Earth and has various components which are sort of listed in the frame on the right-hand side. So that are certain components of the Earth system. For me personally, I work mainly with those three ones. NEMO, that is used to model the ocean physics. So we are talking currents, temperature, salinity mainly. MEDUSA, that is our ocean bio-geochemistry model, which we are using, and NZESM for modeling sea ice. All right, so how do we try to model how do we model the ocean? So it's a simple approach. So we simply divide the globe into small rectangulars. So in terms of for the Earth system model, we use a so-called tripolar horizontal model grid, which is shown on the right-hand side. This grid is simply known as E or K1. So there are small rectangulars, and there are two poles, one over Siberia and one over Canada, and then there's a third pole sitting over the South Pole. So the horizontal resolution of this configuration is 1 degree, so approximately 100 K around the equator. It varies a bit because this grid is not slightly distorted. So there are regions which are higher resolved. And then, because the ocean is not just one layer, it's a big body of water, we have 75 vertical levels. And most of them are illustrated on the left-hand side. Most of those levels we have in the surface layer. That's again due to the fact that a lot of variability is happening in the first 200 meters or so, and we like to model those processes more accurately. So more of those layers are in the first 200, 500 meters, and then those grid spacing becomes slowly bigger with time. All right, so I have sort of motivated how we try to model the ocean, and and also demonstrated, okay, we like to have eddies, or the effect, at least the eddies, the effect of eddies resolved in those simulations. And there's a bit of a mismatch, and that is illustrated up here. So on the right-hand side is sort of illustrated a grid box in this Earth system model configuration. So it's at 70 degrees south, that's sort of deep south region. Grid sizes of, in this configurations, are around 30 by 30 kilometers. All right, so that's fine. Unfortunately, it turns out eddy parameter or eddy diameters in this latitude band are around 7 to 12 kilometers. So that's the blue circle on the top. And so our grid is not, our current grid is actually not able to resolve those eddies explicitly, because it's simply, it's impossible. All right, so that's the reason why there is an eddy parameterization in the current model setup. But my specific task in the Deep South was to really understand how important are eddies for the global scales. And fortunately, NEMO has a nice capability which is called local grid refinement. So that means we can sort of subdivide those one model grid cell into smaller ones. And there are some technical issue or technical limitations. So we can, for example, divide it by a factor of 5. So now we have a grid by 1/5 of the degree, but that is still not enough to eddy or to model the the blue eddy on the top. All right, but if we now further subdivide this domain again into 3 parts, then we end up with 1/15 of a degree, and that is now covers the eddy with 4 grid cells, and that is our criteria which we have to fulfill to really model an eddy explicitly. All right. So how does this now look in practice? So that is sort of unboxing a new model. So I developed, as part of the Deep South, a high-resolution nested model, and I call it ROAM15. It becomes in a second clear why it's called like that. So it's based on our global 1 degree ocean model, which is fine, and then has 2 of those nests. So the first is bounded by this light blue box, which you can see. So it covers more or less the entire South Pacific, I would call it, with a resolution of 1/5 of a degree. So grid sizes are 15 to 10 kilometers approximately. And then within this domain, so that is sort of our target region for the Deep South, Ross Sea region, we have a second nest, which is the magenta or purple box, and that has a resolution of 1/15 of a degree. So grid size is 2 to 3 kilometers. All right. So now with this setup, we are now able to resolve those mesoscale eddies in this region explicitly. And there's one interesting component of the NEMO, of this physical model as well, which is called two-way nesting. So that actually means that all these different grids are actually coupled together. So that means eddies in this region, which Ross Sea region, are feeding back to a global scale. And that is a really interesting tool, because now you can understand how important are eddies in this region for global scales. And that is what I'm really interested in. At present, I performed a long hindcast, so from 1958 up to present, with this model setup. So hindcast means we use atmospheric boundary conditions and try to model past climate variability and climate signals. All right. So the objectives which I sort of try to objectives are, again, mentioned mesoscale eddies. How do they affect global scales? And in terms of the Deep South, I'm really interested in what are the cross-shelf transports, how important are eddies, because we are now resolving them, and also how is the Antarctic bottom water outflow performing. So dense water is formed on the shelf, and how this is now spreading into the abyssal ocean. All right, so modeling talk. Everyone is expecting a couple more animations. And again, shown is here in a second sea surface speed again in 3 different configurations. So on the left-hand side, you have Again, a model which has just 1 degree of a resolution, so really coarse. And then in the middle panel is a resolution or configuration with just 1 nest, so just 1/5 of a degree. And on the right-hand side, that is the final, our final setup yet, ROM 15 with 2 nests. All right, so let's start the animation. And as you can see, there are dramatic differences. First of all these fast variability which you see in all simulations are windburst events, so that are simply storms which push the surface ocean around. But then you see a lot of mesoscale activity. Already with 1/5 of the degree, you see around New Zealand and in the Southern Ocean part a lot of eddies. But if you zoom further in, so that's the lower panel, for example, the Ross Sea region, you see way more eddy activity in 1/15 of a degree. Although it seems there is already quite a good match with 1/5 of a degree, but if I would zoom further in, you would see clear differences. All right, so we can not only model now surface properties, but also now investigate how bottom properties change. And in this animation, I show bottom water properties. So we look at the glass grid cell before the ocean floor, and in temperature at top panel and salinity at the bottom. Let's start it. On the Ross Sea, you find low temperatures and high salinities on the shelf. So that is characteristic for high salinity shelf water. And this water is now flowing into the abyssal ocean, into the Southern Ocean. On the left-hand side is again the coarse model, 1 degree, and on the far right-hand side, the high-resolution model. And you can again clearly see that those mesoscale eddies are influencing this downslope process of dense water from the Ross Sea into the abyssal ocean and influencing large-scale density gradients. And I would claim it's way better or more realistic than in the high-resolution model than in the coarse one. Okay, and why is this the case? So it's sort of illustrated in the bottom panel here. So we have this dense water sitting on the shelf, which is sort of our Antarctic bottom water, and now this water has to descend into the deep ocean. So it's formed on the shelf, but has to descend, and every time it descends, so along our model bathymetry, which looks a bit like small staircases, it entrains surrounding waters, that are the green circles, and changes water mass properties. So on the left-hand side, that is how it looks like in a coarse resolution model. There are only a few staircases, but on the right-hand side, with finer horizontal resolution, there are heaps of staircases, but it turns out that the entrainment rate, so the rate of mixing, is actually lower if we have higher resolution. So that means with higher resolution, your water mass property at the bottom of the ocean is actually quite more similar to your source on the shelf than it would be in a coarse model. So and that is actually what we achieve now with this higher resolution model. All right, so what are the next steps? For me personally, so I finished those simulations last week, so there's now a lot of model validation to be done, and there are a lot of observations which I would like to incorporate in this work. At that stage, also next year or in 2 years' time, when we get those moorings back, which were deployed during the last Antarctic voyage, might be quite valuable for that. And then there are ideas about climate change scenarios. So how does this system now respond? We have now this amazing tool to sort of ask questions about that, how this system now responds to the climate change in a really realistic setup. And there are also ideas now to couple this model to an active atmosphere. So far, I prescribed the atmosphere, and that will change. And then for me personally, it's again about to demonstrate what do we really gain by having higher resolution. There are already some obvious regions where we see certainly improvements just by having those model runs ready yet. Looking here, or shown is here, sea surface temperature on your left-hand side. That is our coarse degree model, and on the right-hand side, higher resort, 1/5 of the degree configuration. And you see there are resolution influences SSTs, and that in the end also influences fronts, and that will be really crucial for climate predictions for New Zealand. And that is already sort of acknowledged by Marston Fund. So I recently was successful to get some Marston funding to actually study this kind of process. So the objective is to study how the subtropical front will change around New Zealand, and in doing this, I will develop a high-resolution model. So the domain is sort of shown here, and we will push even further to higher resolution. At the moment, we are thinking about 1/20th of a degree, and try to study how the subtropical front will change due to climate change. And I see close benefits for both projects, so this Marston project and Deep South, that they complement each other at some stage. All right, I probably forgot to mention Rossi marine protected area work. There's also something going on in this space, which is also related to Deep South. This project is led by Matt Pinkerton here at NEWA. And so the main objective of this project, which I briefly like to touch on, is about ecological changes in the Ross Sea region. And that immediately makes it necessary to start about thinking biogeochemistry changes. And so there are a couple of tools which are listed below, which will be used for this work. First of all, also the high-resolution work, which I've done here in Deep South, but also we will now move forward using MEDUSA, so biogeochemistry, global modeling parts or components to try to understand how this ecosystem will change in the future. This messy diagram on the right-hand side shows sort of the components of MEDUSA, which we sort of or which we use to model biogeochemistry changes. All right. So I'm going with time. That's pretty good. So in the last probably 10-15 minutes, I like to talk a bit more about some recent research which I'm doing due to the exceptional warm summer last year. So there was a lot of media attention, and I was now investigating marine heat waves around New Zealand. And using already this model which we are using within the Deep South, that is a useful tool to, for example, model marine heat waves. Left-hand side shows intensity of marine heat waves over the past 60 years. So that's the temperature difference between your 90 percentile of the climatology. And on the right-hand side is the duration of those heat events. And you see there's a lot of variability. Some marine heat waves persist for a bit longer, and also they occur year-round. So it's not just this summer phenomena, but it's quite interesting. And then there is a study which we are currently working on, which simply or really just focused on the last marine heat wave, so 2017-18, so this summer months, and using model output of my hindcast simulations. So the top panel shows monthly means of the sea surface temperature anomalies, November through to January 2018, and we see the marine heat wave peak during December in this model hindcast. And we can use this model now to understand what are the driving mechanisms behind it, and how does how much of the ocean is actually affected by those heat events. And we sort of analyzed the model data and found that during those periods, during the summer months, we had a persistent blocking high sitting east of New Zealand, which caused that the westerly winds, which we are usually experiencing around New Zealand or in Tasman Sea, become weaker. And that is shown on the bottom panel. So those are wind speed anomalies, and those blue regions are negative anomalies, so it means weakening of the winds. And they, especially in the Tasman Sea, match quite well with those temperature anomalies in the top panel. And what simply happened last year was we had simply lower winds than usual, and that meant less vertical mixing. So heat fluxes were still the same, but now because of the less vertical mixing, more heat was piling up in the surface, or led to the surface heat anomaly, while the entire heat content of the Tasman Sea was not much affected. All right, so that is sort of the conclusion of the past heat event. Again, so because I have those long hind curls, I can also look a bit back in time and try to understand, can we actually do a bit more, and try to maybe not fully predict many heat waves, but maybe can we model heat waves, yes or not? So I focus for this particular study just again on the Tasman Sea, because that is where we are probably most interested in, or there is a lot of interest at least. Again, using the 1 degree model, and it turns out I was looking at the heat content over this area, so Tasman Sea, and it turns out the heat content in this region is highly influenced by the meridional heat transport, oceanic heat transport. So talking about the East Australian current brings in a lot of heat into this region, and that is the main driver for heat content changes. That is shown on the left-hand side. It's a slightly messy plot, but that is what it says. All right, and now the interesting thing is we can now link heat content in the Tasman Sea to marine heat waves, and that is shown on the left side again. So the red curve is the heat content in the Tasman Sea and their long-term variability, which we are really good well understand those variability, where it's coming from and what are the drivers, and they match quite well now those heat wave events. So those bar charts show how not how strong, how big the area of a marine heat wave was. And there are, for example, those periods where this drop in the 1990s in the heat content, for example, over this period we barely found any marine heat waves. And that can be sort of been used to now predict heat waves, because again we know what the driving mechanism between for those heat content changes are. That is the East Australian current bringing in heat, and this heat is sort of not necessarily seen at the surface but at lower depths. That sort of should show the Tasman Sea. So we have this heat content changes in the interior Tasman Sea, which we can also not only model but also use Argo floats, for example, to get those heat content changes. And that at some point this simply influences your background state. So for example, if the Tasman Sea is already warmer, then it's more likely that next summer or so those heat anomalies or surface temperatures exceed certain thresholds, because the background state is simply already something else. All right, I think it's slowly time to wrap up. I hope I was able to convince you that oceans play an important role on climate timescales, and there's a lot of things going on also below the surface. In terms of model resolution, I think that's really a key for a lot of, and it also provides a lot of probability, not probability, a lot of ability to improve climate predictions for New Zealand, especially if we are looking at long time scale into abyssal ocean. So we see improvements in the Antarctic bottom water outflow from the Ross Sea region. It has to be verified. That is what I'm working on at the moment. We also see certain improvements by increased model resolution, and I think that will sort of also contribute to improved climate predictions over the long term. And then sort of the science wrap up. So I think meridian heat attraction influences meridian heat waves, and that could potentially be used to sort of predict heat waves in the near-term future. All right, and that is what I wanted to say. Thanks very much for your attention.
Thank you very much, Erik. That was a really interesting presentation. We are going to open up the floor for questions. So if you're in a hub, there is an icon on Zoom where you can raise your hand. If you click on the button that says participants, and underneath that you can raise a hand. So Alex Keeble will see you and let me know. If you're here in the room in Wellington, you can just put your hand up and I'll... Yep, we don't have to use virtual technology. Similarly, if you're in a room but you don't have control of a computer, then feel free just to put your hand up and we'll try and keep an eye on you. So if we don't have anyone raising a hand on Zoom yet, then I'll probably open the floor here in Wellington. So we've got one question from Abba, first of all. So.
Very interesting talk. And looking forward to the results. Do you have any idea at the moment the validation of the virus? Have you looked at it before, or an idea in which direction?
It goes in the right direction. So I can at least state from large-scale quantities, like, for example, Southern Ocean circulation, the entire Ross Sea gyre, that is the region where we have this high-resolution nest covering this region, has certainly improved. So in terms of shape, but also in terms of intensity, so I think we see substantial improvements in this region, and that I think that is a major outcome, and this model provides the potential to be used in a lot of scientific research in this region, because that is quite exceptional, and I think it's also cutting edge at the moment. I haven't seen anything else at the moment in this space.
I'm going to pass the microphone because it will help with people in other locations to hear the questions. Thanks.
I don't know, am I allowed 2 questions? Pretty simple ones. In your nested model of the Ross Sea, is the sea ice a constraint?
There's a proper sea ice model included. Yeah, we model sea ice. I haven't shown it, so right. Because I'm an ocean modeler. No, we have everything. There is a proper sea ice model. There are no ice shelves at the moment, but there could be ice shelves included, ice cavity. All those options are possible. At the moment, I'm prescribing ice shelf fluxes, so freshwater fluxes from ice shelves. So there's a vertical function which sort of is used to spread freshwater around. Yes.
And on marine heat waves,
yeah.
So you were saying that the typical marine heat wave is due to advection of heat, but you were saying that last year's was an atmospheric phenomenon.
Yes, it's simply it's probably, or my personal opinion is that it is really hard to predict SSTs or winds in advance. 1 year in advance will be always impossible. That is my understanding. But we have some handle on that we can predict heat content changes in the Tasman Sea. So that is probably where the potential is to sort of, if we see, okay, slowly the heat content in the Tasman Sea goes up, I mean, that is, for me, rings a lot of alarm bells straight away. We are not going to be able to, you are completely right, so the last heat wave was exceptional. We couldn't have predicted that based on this diagnostic. True, but we know those heat content in the Tasman Sea doesn't change from year to year, or not substantially. There are long-term modulations, as you've seen, and we know what those long-term variability is caused, or causes those long-term variability. Yes.
Do we have any more questions from the floor? Yep. In the front row. Oh,
Oh, maybe.
I saw that hand first, so maybe we'll go there. Oh, did you?
I was going to ask one.
Oh, sorry. Okay.
Since I had it in my hand. Just on that heat wave in the Tasman Sea,
Yes.
the atmosphere had a lot of highs that year, so there wasn't actually much wind over the sea, so there wouldn't have been much mixing. Would that have had an influence as well?
I mean, that is what we concluded. So in terms of, there was low wind speeds over the Tasman Sea, and heat fluxes were the same than the years before, but simply vertical mixing was lower than it used to be. So heat flux is the same, but you spread the heat over a smaller water column, and that caused this massive heat wave.
Thanks. So I saw the front row, and then Phil, and then someone in the back row.
I'm just interested in the model resolution, the nested grids. I have no doubt that's going to improve a lot of representations of a lot of processes, but where's the limit with it? Are you at the limit of what can be done computationally, or could you put an even finer grid in the southern Ross Sea?
There are no limitations. No, there's. It's still possible to do even higher a nest in a further nest. Yes, I know colleagues of mine, they have pushed those techniques up to 1/60th of a degree. It is the question if that is really necessary. I think at the moment on those timescales which I'm interested in, 1/15th is probably how far we should push it, how far it is reasonable. But if you have specific research questions which require more, that is still is also possible.
Thank you.
Do we have any from any other hubs? No, so we're just going to keep going at Newark, Wellington, here and in the front row.
Thanks, very nice talk. So just a very basic question about ocean models. How do you initialize them? Do you take satellite observations, or where do you get the data from to know where to start?
Okay, I mean, that's, to initialize oceans, we use a crude assumption. So we use climatological fields for temperature and salinity. So what is basically done, somebody took all ocean observations together, temperature, salinity, and produced the climatology. And that is sort of where those models are starting from. There are no, I mean, satellites are playing a role in terms of the atmospheric forcing. So for this model, which I'm running at the moment, it's a forced simulation, and this has satellite data included. So for example, I don't know how they really derive those forcing products which I'm using, but the satellite data is merged in them somehow.
Okay, would you like to just introduce yourself first? Okay. We should have done that earlier. And then after that, we're going to go to at Argo University. They'd like you to repeat something from the presentation, and then if we've got time, we'll come back to the other questions.
Okay, hi, it's Emily Lane here. Thanks, Erik. It was a great talk. Just when you were talking about the finer grids, I know often when you're with modelling, the subgrid scale parameterizations are dependent on the size of the grid. So as you're going down to those finer grids, do you need to sort of retune how some of your parameterizations, or are they valid over the scales you're looking at?
Yes, you have to adjust two parameters, which are viscosity and diffusivity. That are the only two parameters which you have to modify. Everything else is sort of done within the model code. So I don't change the physics itself. I mean, which is reasonable. If you have finer scales, I mean, things are simply less diffusive than on coarser model grids. Yes.
Okay, Adrian wanted you to go back to the presentation. Sorry, I'm just trying to work out how to do that. That's the problem. Exit screen.
So we were just wondering if you could highlight the use of the high-grade grids, because we were looking at the pictures. We could see some differences. We could also see some similarities when we point at points to show us where we should have been looking.
Has somebody understood what he...
So it's the high resolution slide where you were pointing out differences, but he wasn't sure where he was supposed to be looking. So if you choose the slide...
High resolution.
It's not...
So I think this was the Rossi cutout and the comparison of 1 degree, 1 fits.
Yeah, okay. Let's see if we bring it up. Any moment. I think we need to go back to this thing and probably, if that works.
We're sharing our screen here. We're doing a slideshow.
Erik,
yes.
Adrian is asking about slides with 1 degree to 1.15
Yes.
degree.
Yeah, I mean, we have it here, but we at the moment
make it come up there,
struggle to bring it back on the screen.
No problem. Yeah, I can ask the question later.
Did you have another question?
Here we go. Maybe.
I don't know if that will work.
No. So we seem to be unable to bring up this slide again. So it was simply what I wanted to show with this animation. There are a lot of mesoscale eddies, and especially in the high resolution model in the Rossi region. And not only in the Rossi region, also in the Amundsen Sea. That is also where a lot of research interest is recently drawn into or is going on. So I think especially mesoscale eddies in this region are really important to spread around icebergs, freshwater fluxes. That are the main drivers in those regions, and I think this model is performing way better than we would have it in the 1 degree, for example.
Okay. Are there any more questions from other rooms? No. Okay. So.
Oh yeah, Adrian.
Oh, again.
So did you still have a question, Sarah?
I have a question that occurred to me now. Right, so there's some processes in the atmosphere and ocean parameterised because they're too small scale. How far are you away from being able to high resolution to resolve all the eddies that you need, basically? So is it a factor of 5 out thing, or is it a factor of in terms of computational time? We can't hear you.
Okay. So I think your question is about how far we are away from resolving mesoscale eddies. Is this your question?
Yeah, and just routinely being able to do that.
Routinely. So as a matter of course, you want to resolve all these eddies.
Yes. I mean, I think with this model configuration, which I've shown, we are able to resolve eddies in the Ross-Amundsen Sea explicitly. So there's no eddy parameterization at that stage necessary because we resolve them. So in other regions, you don't need to go to 1/15th of a degree to resolve those eddies. So in lower latitudes, the eddy radius or eddy diameter is less, or is way bigger, and you probably get away with 1/10th of a degree, or even in some regions maybe less.
Adrian, I think, has another follow-on question.
He's really interested. Okay, cool.
Adrian, do you have a follow-on question?
Yeah, Wolfgang here. I would have one question about the coupling of the sea ice and the ocean. So how is the wind stress via sea ice coupled to the ocean model? Can you tell me something about that?
The coupling between ocean, sea ice, and atmosphere is done by using bulk formula. So I'm sort of prescribing wind speeds at 10-meter surface in this forced simulation, and then using bulk formula, then they compute how much wind stress it is. So it takes into consideration sea ice velocity and also ocean velocity to compute the drag and wind stress itself. I hope that answers your question.
Okay, so we're going to come back to Wellington. We did have, sorry, David, we had Sarah and possibly Olaf and Sue. And then if we've got time, David. Yeah.
So my question is,
yes.
In your first slide, in your last slide, you said you were going to tell us about carbon. And I know, and I know that you haven't done the whole biogeochemistry simulations yet with this configuration of the model, but I was wondering if you could speculate on how you anticipate the different resolutions are going to affect carbon exchange.
Okay, I share now my personal opinion, so a lot of people probably will disagree. In terms of mesoscale eddies, it has been shown by other colleagues that the response in the Southern Ocean is resolution dependent. For example, in coarse model resolutions, if you increase the westerlies, which occurs at the present due to climate change, they see a spin up of the ACC. Okay, that is what coarse models tell them. That is what Earth system models predict at the moment. And then they run the same simulation with eddy resolving. And they found nothing happens. I mean, the only thing which happens is that you produce more eddy mixing. You generate more eddies and you don't see any speed of the ACC at all. And that is really interesting because at that time those resolutions or responses completely diverge. And how that influences carbon, I have no idea.
All right, so the high-resolution model that you introduced today covers roughly, I suspect, 1/3 of the Antarctic coastline. The other 2/3 are not covered. So in terms of global modeling, that's slightly sub-ideal because you partially solve the problem and partially you don't. So what's your suggestion how to address this?
Again, I think this model at the moment, I need to prove that we can definitely improve, or that resolution really matters in this region. So that is what I have to demonstrate. A lot of people tried to solve this issue completely for the entire Antarctic. The people have done, especially for Antarctic bottom water production and outflow, Lagrangian blobs and stream tubes and all kinds of parameterization, and they are not satisfying. And so in the end, they tried and failed. And at the moment, we have a new supercomputer, and maybe somebody, a new project comes up, and we do it over the entire Antarctic in the next stage, maybe, if there is enough interest and have that running. Yes, it's possible. At the moment, it was simply highly motivated by our regional focus on the Ross Sea. Yes, but if there is a lot of interest in Weddell Sea or global scales, I think there are no limitations. People have run this model in a this nesting approach in the entire Southern Ocean covered setup, so that is not an issue. Now the question is there enough research interest, enough benefit to really make it work?
We've about 2 minutes. It'd be great if we could squeeze in the last 2 questions. So,
Okay, hi Erik, thanks very much for a great talk. Just to go back to the marine heat wave, and apologies if this was covered already, but you obviously gave us the oceanic sort of perspective, but I'm just wondering, was there potentially a role for the heating, direct heating that would have resulted from the fact that there was so much high pressure and clear skies, or would you expect that to be negligible in comparison to the oceanic component?
The oceanic heat fluxes, they were quite similar to previous years, so I haven't seen any real influence that more clear sky conditions were a real trigger for the oceanic component. How that it probably has influenced New Zealand, temperatures over New Zealand, that for sure, but at least for the ocean, like based on my simulations, there was not much change.
Yeah. This is a sort of a more general question, not so much a deep south one, but a global climate question, I guess, thinking about sea level rise related issues. One thing of great interest, I guess, is the exchange of heat between the Southern Ocean and the ice caps. Do you think, and are there people working on using these high resolution models to start to explore that question?
Yes, because a lot of people are interested in, especially this question, so sea level rise, ice shelves, instability of ice shelves. And it's again about eddies are the main driver for which transports heat across the boundary shelf or cross-shelf processes across this boundary. And so I think they are now also pushing towards higher resolution. There's always a bit of unfortunately, disconnection, because at the same time, ice shelves, sea level rise happens on long time scales. So there's always a bit of a trade-off. How much you can really afford higher resolution to have really long simulations. We are talking thousands of years. I mean, that puts a couple of constraints on that. But yes, for short sensitivity studies, I mean, that is what you need to investigate. Cool.
Thank you, Erik. Obviously a really interesting topic. I think everyone needs to find Erik in the cafeteria to keep quizzing him. Thank you to everyone who zoomed in from various hubs around New Zealand and also individuals. And thanks to everyone here at NEMO Wellington for coming and supporting us. Keep in touch and let us know if you need to find out more about the Deep South Challenge. Thank you. We had lots of time.